And what we end up with is this: PV over T is a constant, because it's a fixed container, N is not changing, and R is a constant, so NR is a constant. So that means that P initial, V initial over T initial has to be P final, V final over T final. Right? If it's a constant, it's the same at the beginning as it is at the end. The pressures are the same, we just said that. And so the temperature goes up. Then the final volume has to be greater than the initial volume. So I think that answer is consistent with ideal gas law. You may have been tempted to use the ideal gas law back for that previous one with the two, for part E. You may have been tempted to use PV equals nRT, try to figure out, how does the pressure compare with these two cylinders? What's the problem with that? The second cylinder is different. It has a different gas, different number of moles. So the cylinder is identical in terms of the shape, the weight of the piston, things like that. But they told us it's a different sample of an ideal gas. So N could be different. So that changed it. That meant we couldn't use PV equals nRT. There are too many unknowns. Whereas in this next case, on the top of page 228, where you're taking the cylinder out of an ice bath and putting it into a boiling water bath, then the same cylinder, the number of moles is fixed, so we can use PV equals nRT is a little more helpful there. All right, and what's constant? And what can change in this type of process? What's constant? Pressure? Is that what you said? Pressure is constant. The piston is free to move, and its weight's not changing. Atmospheric pressure is not changing, so it will always keep the pressure inside the same. Pressure's constant. What else? N, yeah, the number of moles, the amount of gas. What can change? Temperature and volume. Okay. So let's look at what the students are saying here. Student 1 says, according to the ideal gas law, the pressure is proportional to the temperature. So far, so good? So far, so good, right? Since I increase the temperature of the gas, the pressure must go up. Yeah, the problem is that they're missing out on some other things, right? The pressure is proportional to T, but it's inversely proportional to V. So student 1 is ignoring the fact that the volume is changing. They're saying pressure is proportional to temperature, temperature goes up, P must go up. But in this case, as the temperature went up, the volume also increased. So that's their mistake. Student 2, that's right. Since no gas entered or left the system, the volume did not change. So the pressure must have increased. So they're correct. No gas entered or left the system. But that does not mean that the volume is fixed. Because if we excite the gas that's in there, it will try to take up a bigger volume. It wants to expand, thermal expansion. So it tries to take a bit bigger volume. In this case, the piston was free to move, so it allowed the gas to take up a bigger volume as we increase the temperature. Page 229, the top of page 229, it's introducing PV diagrams. So the idea here is plotting the states of a gas on the PV diagram. What do we mean by a state? That means when it's at a particular pressure, volume, temperature. That's the state of the gas. And we can move it between states, right? We can increase the temperature. We can change the volume, change the pressure, change all three. Change them one at a time. So there are different ways to move from one state to another state on a PV diagram. And we use these a lot. It's a good tool for us. Now remember, this cylinder with the piston, it's not just an artificial construct that we use because it makes it easier to analyze gases and how they change. It does do that, but it's very similar to how we use gases to do work. So in a car engine, in a gasoline internal combustion engine, there's a cylinder with a piston that goes up and down, and the gas is compressed and it's ignited and it heats up and it expands, and it goes through cycles very similar to what we'll be talking about and illustrating on a PV diagram. So at the top of this page, this is an introduction to PV diagrams, and they tell us an ideal gas processes are often represented graphically. For instance, a PV diagram is a graph of pressure versus volume for a given sample of gas. A single point on the graph represents simultaneously measured values of pressure and volume. These values define the state of the gas. So they want you to draw on the PV diagram the process from the previous section. The one where it started out in the ice bath and ended up in the boiling water. So what do we get? It starts out at some initial pressure and some initial volume, and then what happened? The volume increased, and what happened to the pressure? Stayed the same. So at constant pressure, it changed to V final. Something like this. Horizontal line. Now they give us a PV curve with four states indicated. And what they want us to do is rank the temperatures of the gas in those four states from largest to smallest. What's the thought process here?
T is proportional to P times
because N and R don't change, so T is proportional to P times V. So for A, what do we get? 4 times 1. For B, 3 times 2. For C, 1 times 3. And for D, 1 times 4. Is that right? So the temperature at B is the greatest. Temperatures at A and D are equal. And the temperature at C is the lowest. Are we consistent with the ideal gas law? Well, we use the ideal gas law to find that, so I think the answer is yes. Is it possible for the gas to be in a state in which it has the same volume as in state B and the same temperature as in state A? If so, mark it on the PV diagram. Is it possible?
Yes.
So what do we have? We say P times V has to be 4. That's the same temperature. And V was 2. So at P equals 2, V equals 2, we get our point, right? Two, right there. I'm just calling these arbitrarily 1, 2, 3, and 4. Okay, getting a feel a little bit for the PV diagram. Okay, let's do the last page. Section 4. Two cylinders of the type described above contain hydrogen and oxygen. Both cylinders have been in the same room for a long time. Their pistons are at the same height. Compare the volumes of the gases in the two cylinders. How do the volumes compare? Same, right? The pistons are at the same height. Compare the temperatures. Same, they've both been in the same room for a long time. Compare the pressures. Same, because the pistons weigh the same and the atmospheric pressure is the same, so the internal pressure has to be the same. Compare the number of moles. What is it? Same? Because P, V, R, and T are the same, so N has to be the same. So it says a student looks up the molar masses and finds the values 2 grams for hydrogen and 32 grams for oxygen gas. So what does molar mass mean? Grams per mole, right? 1 mole of the gas weighs this many grams. So how would you compare the two masses? oxygen is, what, 16 times the mass of hydrogen? Since hydrogen molecules are so much smaller than oxygen molecules, is that true? Yes. There should be more of them in the same volume. Doesn't work that way. Gas molecules are completely independent of one another. They fill whatever volume you put them in. If you have a balloon, helium balloon, walk into this room, let go of it, the helium comes out. In a short period of time, the helium will be uniformly distributed throughout the room. It fills whatever volume you put it in. So just because we have more, just because they're smaller or bigger doesn't mean they're going to get more or less in there. They're not. We're not limited by the size of the atoms, right? They take up a tiny, tiny volume compared to the volume of the container. They move around and fill the volume because they move around and fill whatever volume you put them in. They're not limited by the size. And student 2 says, since n equals 2 for hydrogen and equals 32 for oxygen, there must be more oxygen molecules. So they're getting n confused with molar mass. Right? Molar mass is the number of grams that a mole weighs, and little n is moles. So if n was 1 mole of hydrogen, it would weigh 2 grams. If n was 1 for oxygen, 1 mole of oxygen, it would weigh 32 grams. You don't want to confuse the number of moles with the grams per mole. Okay? All right, hopefully this was a good chunk of review, and it helps set the groundwork for how we're going to use this in physics in this chapter. Now we want to review, so that was part of the equation, right? We have internal energy equals Q minus W. That was the first law of thermodynamics. So we've talked a little bit about how we can change a gas from one state to another, sometimes by adding heat, like taking it from an ice water bath into boiling water. We're adding heat, taking it from one state to another. And we reviewed a little bit of what we needed to know for that. Now we need to review a little bit for work, because the other thing we can do is do work on the gas or have the gas do work on the environment. So we need to review work a little bit. We went over it last, whenever it was, back in 2A, chapter 7 or 6 or something like that. So we need to review work a little bit. So we'll start off on page 231. Here I have to hand it out, don't I?